We're supposed to find the time when the instantaneous velocity of the pebble equals the average velocity of the complete fall. So this pebble is falling. Its position is in a negative quadratic, so maybe it looks something like this. We don't need to draw this side because that'd be negative time. So average velocity of the complete fall. So here's the starting height. Here's the ending height of the pebble. If we were to draw a line between those two, that's called the secant line. That secant line represents the average velocity over this interval, right? So the mean value theorem says, hey, if you've got a continuous interval and it's differentiable on that open interval, then you can find out another location where we've reached the average velocity. So over the interval, maybe it's dropping at 10 feet per second. Maybe that's the slope of that line I just drew here in red. The mean value theorem says, hey, there's another place. Looks on my graph, it looks to be somewhere right here. Maybe that's like x equals 1 or 2 or something like that. There's some other place where we've reached that average velocity. You know, here, this is not the average velocity. That's falling faster than average. Here, this is falling slower than average. But if we draw a tangent line right about this part of the curve, then it's reached its average velocity over the entire flight of the ball, or pebble, whatever it is. Okay, that's the concept of what we're doing. I've got the mean value theorem right over here, and that's what it says. It says there's some c where the instantaneous velocity is the same as the average slope over the entire interval. So one thing we need to know is we need to know when this pebble hits the ground. We know it starts at t equals 0, right? Because it starts at 54 feet in the air, so if you plug in t equals 0, you get 54 feet for the height. We need to know where it ends. That way we can have an interval for the mean value theorem. So to find out where it ends, we're looking for where the height is 0. So if you solve that equation, divide 16 from both sides, so negatives cancel out. Divide the top and the bottom by 2, so that's 27 over 8. Then use a square root on both sides. So at the square root of 27 over 8, this thing has reached the ground. So now we know our interval. Now we got to plug in the information to the mean value theorem. Okay. First, the derivative. The derivative of s of t is negative 32t. And then if we plug c into it, like this notation says, that's negative 32c. And just keep in mind what c is. C represents the time when we've hit that average velocity over the interval. Now the y value for b, it means when t equals 0, what's the y value? It's 54 feet, right? That's the response variable. And then when we hit the end of the interval, when t equals the square root of 27 over 8, we're at 0. But this part's going to be a little messy. Oh, I have those reversed. Okay, that's a big sin here. It does matter the order because you have to stay consistent with the numerator and the denominator. And just so that we stay consistent with what the textbook does, b is the right side of the endpoint. So I should actually have this as 0 subtracted by 54. If you kept the same order in the bottom, that'd be fine, but I should be repeating the same pattern with the intervals. B should be the largest t value. So that's square root of 27 over 8. You know something was wrong if you got a positive slope, you know, when you plug your answer in, right? And then A is the start of the interval, so that's t equals 0. So that's what everything looks like when it's plugged in. So it's negative 54 over the square root of 27 over 8. And we're trying to solve for c, so I'm going to multiply both sides by negative 1 over 32. Remember, c isn't the slope, c is the location when the instantaneous slope is average. So some simplification. The negatives can cancel, negative times negative. Then I got 54 over 32. That's 27 over 16. So 27 over 16. And I'm going to move this fraction off to the side. That's the square root of 27 over 8. I'm running out of room. Okay, that's good enough. Okay, so we'd flip and multiply, so that's 27 over 16 times the square root of 8, just breaking up the square root, same thing. So you got 27 to the first power over 27 to the 1/2 power. That leaves you with the square root of 27 in the numerator. And then what could we do with the square root of 8? We could simplify the square root of 8. That's 2 square roots of 2. And in case you're wondering where that came from, the square root of 8 is the same thing as the square root of 4 times the square root of 2. So that gives us 2 square roots of 2. So we already took care of the 27s. 27 to the first divided by 27 to the 1/2 makes 27 to the 1/2. And you can multiply inside the radicals, but we could also simplify this. So square root of 27 times 2 makes square root of 54 over 8. I think we're done now. That's the time when the pebble is falling at an average speed, an average velocity I should say. It's falling at an average velocity over this interval. Oh wait, can we simplify? Square root of 54, that's divisible by 9, right? I missed something here. Yeah, so that's square root of 6 over 8. So this is 3 square roots of 6 over 8. Hopefully Newton likes that.